Hello and welcome to Physics for Play. In today's episode, we're going to show how you can use the Fourier series to decompose a standing wave into its normal mode components. Let's get started. So we are going to to do this, we're going to just run through an example. And this example I'm pulling from one of my old problem sets. It's from a source by Bekefi and Barrett called Electromagnetic Vibrations, Waves, and Radiation. It's kind of an old school book, and I think it's actually pretty good, especially for the time. I enjoy it quite a bit. We're going to be looking at problem 211 in Bekefi and Barrett. So if you look at that problem, it says you've got a guitar string of length L that is plucked a distance d from one of the ends, and you can see a picture of that guitar string being plucked right here. And it says if its initial shape at time t is like that illustrated in the figure, show that the displacement from equilibrium at any subsequent time is given by this function s of z and t. I'm going to make that a little bigger since it's a little hard to read. It's a little fuzzy. But you've got s of z and t, and you can see your Fourier series right here. And it says that it's going to be s of z and t, where the amplitude is given by this function right here. It has a follow-up question that asks, what must you do to suppress the eighth harmonic, where m in this Fourier series equation, the mode number is equal to the eighth mode. So we're going to go through how to do a problem like this. So we'll go through the solution, and then we'll also look at, we'll do some extra credit questions looking at how to visualize it, how to animate it. And then for a guitar string, we also have the luxury of being able to play what it actually sounds like. So we'll take a look at that. So the first thing to note is that any vibration of a plucked string can be represented as a superposition of an infinite number of normal modes. So no matter what the shape, what the initial shape is, we can plot the evolution of that for all time using the Fourier series. And we can use that pretty much using the equation that's shown here, but pulling the same equation out of the text. If you happen to have a copy of Bekefi and Barrett, that's equation 2.45. And you can see it's a sum of sines and cosines. Here, you've got some amplitude. You've got a sine term that's dependent on z, where z is the distance along the string, L is the length of the string, M is the mode number, pi is the usual 3.14159. So this gives the spatial dependence of the string. And you've got a second term here as well. That gives the spatial dependence. And then you have the time dependence, which is given by the cosine times that mode number again, times the angular frequency omega naught times t. And then a similar thing here, but because you want to have both the even and odd functions, you have both a cosine term and a sine term. So that'll get you a complete description. The reason you do not have sines and cosines for the spatial term is because both ends are fixed at s equals 0, and your cosine terms will go to 0. So those will zero out. So we just have an infinite sum of this sine times a cosine, and then the sine times the sine. Now we can already start to see that this is looking like the what we're told we need to find for the form of the solution. But to get this form, we really need it to be that the sine terms here are 0. So we're going to make the assumption that since the string is plucked, it starts from rest. If that's the case, then the initial velocity has got to be 0, and that's going to be 0 at all points along the string. And the only way that can happen is if all coefficients bm are 0. So that's why this second sum has got to be 0. You can see this by taking the time derivative of this term. Time derivative of a sine gets you a cosine. A cosine at time t equals 0 will give you something that's non-zero. So you'll have a non-zero velocity if that's the case. So you need to set your BMs, your coefficient B sub m equal to 0. So that's how you get rid of that second summation. But then the question is, how do we figure out what this amplitude is? And is it equal to the amplitude that's listed in the problem here? This 2al squared divided by m pi squared d times l minus d times the sine of m times pi d over l. And to see that, we can use what's known as Fourier's trick. So if you have a differential equation book, or especially any physics book that covers the Fourier series, you will see that Fourier's trick can be determined. Basically, you figure out what these amplitudes are by multiplying your function times the sine of m pi z over l. So the first thing I'm going to do is set up a piecewise function. So I'm taking a piecewise function where I'll let you work this out on your own, but the piecewise function is really just two straight lines. So I've got a straight line going up over here, which eventually achieves a height a at z equals d. So for that, we type in, we just need to have a slope of a over d. You can see the rise is a, the run is d, so your slope is a over d. And that's valid for z less than d. And for any value of position that's greater than d, so that's this region over here, that is going to give you a different value. So for, for z greater than or equal to d, you have a different slope. Here your slope is going to be negative now because it's sloping down. And I'll let you work this out. The slope will be a over l minus d. And then you have some y-intercept over here that you can also figure out. That's just listed right here. We'll go ahead and plot that in a, actually, why don't we just go ahead and define that and plot it so you can see that I'm not lying to you here. And I'm going to actually have to put in some values for a. So we'll set a equal to 0.1. We'll set d equal to 0.2. We'll give the string a length L, which is going to be 1. And I think that should be that. I think that should be good enough. We'll go from z is 0 to 1. And there you go. You can see you've got a shape that looks like what's in the picture with our piecewise function. But now we want to use Fourier's trick. So to figure out what the amplitude is, what you do is you take the function that you're trying to approximate. So in this case, we've defined that function to be s of z over here, our piecewise function. We multiply that function by the sine of m pi z over l. And what that's going to do is for any Fourier term, for any mode that has a mode number m, this will give you something that is non-zero. For anything where that is not the mode number, where that it does not have a mode number of m, it'll give you, this will average out to 0. So effectively, this is pulling out the certain modes, the amplitudes of certain modes. So we're just going to do this trick. And I'm also going to be using the assuming function here, just because Mathematica is not going to make any assumptions unless I explicitly tell it to. So it's very basic assumptions we're going to make, and this will simplify our output by making these assumptions, which is why we do it. But we're going to say the length of the string obviously has to be bigger than 0. The position along the string obviously has to be bigger than 0, and it has to be less than length L. I obviously can't pluck the string anywhere that the string is doesn't appear. And we're also going to say that the mode number is just going to be an integer. When I do that, if I run that code, it'll simplify the output for me because I put those assumptions in. Again, this is the equation for the amplitude, which in this case is my a sub m number. And you can see that this form looks exactly like the form that is given in the initial problem. So we can see, let me go ahead and get rid of my graph for a second. We can see we've got a 2al squared in the amplitude. We've got a 2al squared in the amplitude that we got from Fourier's trick. We've got a sine d m pi over L. Here we've got a sine m pi d over L, which is identical. Then in the denominator, we've got an m squared pi squared. Here we've got an m pi squared total quantity. Here we've got a d times d minus L with a minus sign in front, which is the same as the d times L minus d in the denominator over here. So we've proven the first part of this problem. The last part of this problem, as we said, it wants to know what do you have to do to suppress the eighth harmonic. And to see what that looks like, we're going to actually plot the eighth harmonic, the amplitude of the eighth harmonic as a function of d. So if we look at the amplitude we got, we can see that our amplitude depends on d, which is where we actually plucked the string. So depending on where you pluck the string, you're going to get a different amplitude. And we can actually pick this out by plotting what that amplitude is. And we're also going to plot the shape of the eighth mode, and we'll see why we do that in a second. But here I'm going to choose some parameter values. I'm going to just choose the string length to be L. I'm going to pluck the string a distance d along. Actually, I'm going to just delete this because I don't even need that here. I'll do it in the function. So I'm going to plot my amplitude, which I just pulled, this amplitude that we just computed. I'm going to plug in some numbers here. Again, we'll choose a string length of 1. We'll pluck right in the middle of the string, so we'll pluck halfway along. We'll pluck it up a distance of 1/10 of the length of the string, and we're going to plot this for the amplitude for the eighth mode. And we'll plot that in red, which you'll see here. And I'm actually showing two plots. I'll show what we've got here, but you can see that the plot, if you plot for a value of the amplitude where you're plucking very close to one end, you can see you've got a high amplitude, and you can see your amplitude goes from positive to negative, crossing the axis. So at these certain pluck positions, so we're plucking at a distance d along the length of the string, and at certain positions we get 0 amplitude. And what I've done here is I've wrapped this whole thing in a manipulate where I can change the value of d where I'm plucking. And I'm also going to plot the shape of that eighth mode. So right now it's plotted in blue, but I have no shape for that mode here because, well, I've set d equal to 0, so I'm plucking right in the middle of the string. And if I pluck right in the middle of the string, I suppress that eighth harmonic. There are other places that I could pluck. So if I pluck at different points along the string, if I pluck very near one edge, you can see I've got a pretty large amplitude. As I pluck, let's see, it looks like I've got another 0 here. If I pluck a quarter of the way along the string, and you can see if I set d equal to me plucking a quarter of the way along the string, the amplitude goes away. Same thing if I pluck an eighth of the way along the string, it goes away. But if I move just off of that, you can see we start to get some amplitude again. So this kind of shows a nice visual of how, you don't have to just rely on doing things by pen and paper. You can do some pretty quick analysis and get much more of a visual representation into what's going on by actually using some software and plotting out the different functions. And in fact, we can do quite a bit more than just that. We can treat this as an extra credit problem. Obviously, this wasn't asked in the initial question. But what if we wanted to visualize how good the Fourier approximation was? Well, I can, even without the problem telling me what the answer is, I can just use Mathematica's Fourier sine series to do that work for me. So I'm going to do a Fourier sine series for the initial shape of my string s of z. That's going to be as a function of z. I can tell it I want to include n terms where I'm setting this function up so that I'll choose n equals 10 here, but we can set n to be whatever we want. So we can choose as many terms as we'd like in the approximation. And then you need to set your boundaries and your parameters in the Fourier sine series. So these parameters I'm choosing so that our string has a length L. If you are interested in how this works, you can just pull up the help menu for the Fourier sine series and just look in the detailed options for how that Fourier parameter works. But I won't go into it here since this video is already going to be a little bit long. But again, we'll want to make some assumptions, and the assumptions will just be that the string has a length that's greater than 0. I'm plucking somewhere along the length of the string, so my d has to be between 0 and length L. And again, the mode numbers are going to be integers. What I'll do is we'll choose some parameters. We will plot our s of z, our actual function, and then our approximation to the function for those parameters. And then we're going to wrap that in a manipulate where we'll change how many terms we include in the Fourier series approximation. So I'm going to go ahead and run that. And I actually need to tell it what the Fourier approximation is going to be. And we'll visualize what that looks like for 10 terms. This will run for just a few seconds because the sine series is relatively complicated to run. So here's the first 10 terms in our series, and you can see it looks very similar to what we had up here, but now we've plugged numbers in. So we can see that for one term, it's not a very good approximation. So here's what the actual shape of my plucked string looks like. My approximation, not very good if I only have one term in the approximation. If I include a second term, you can see that gets a little bit closer. It's starting to look a little more peaked near the d is 0.2, which is where I plucked the string. For 5 terms, you will see it'll get a little bit closer. It doesn't quite match near the peak, but you can see it oscillates a little around the correct value there. If I go up to 10 terms, it'll take a little longer to evaluate. We'll know it's updated. There we go. You can see that for 10 terms, it gets even closer. Now 20 terms, again, it's going to take even longer to evaluate. But I'll see from my plot, I've actually labeled the number of terms in the approximation. But when this evaluates itself, I should see this n equals 10 get updated. And I should see the peak get even closer to where we are before. And this is one of the big advantages to doing something like a Fourier series approximation is that you can see even with 20 terms, this pretty rapidly converges on the actual shape of the plucked string. So it's one of the big powers of Fourier series. So for our little extra credit number 1, we can visualize how good of an approximation that Fourier series is as we include higher and higher order terms in that approximation. But we can do even more than that. We can actually animate what that's going to look like. So again, I'm going to set up some parameters. I'll pluck the string an eighth of the way down its length. Here I'm going to use an animation, and I'm going to plot the shape of my thing. Here I'm actually just going to write out the term so it doesn't have to compute the Fourier series on its own. I'll give it help. I'll give it help since we already know what the answer is. And we'll include the first 20 terms. So we're going to plot this for the first 20 terms in the Fourier series. And then we're going to animate what that looks like for the first 50 seconds. So we'll go ahead and run this. And you can see when you let that string go, this is kind of like a time-lapse video of what plucking the string at that position is going to look like. And if I wanted to pluck it at different positions, so if I wanted to pluck it, let's say halfway down the length, you can see what that would look like as well, and how that standing wave would reflect at the different boundaries. So already we have a very powerful visualization tool. We've got a great approximation technique with the Fourier series. We can visualize that very easily. The last thing I'll do as an extra credit problem, since this is a plucked guitar string, you might ask, what does this actually sound like? So we're going to do a few different things here. We're going to play what a MIDI sound for that sound is going to be like. Then we're going to play the Fourier series approximation of that sound that we created, and we'll make an audio plot of what that sound looks like. Mathematica has a nice function called sound note and another function called sound, where sound note will actually tell you, it's an object in Mathematica that will tell you what a sound is actually like, and we can do that for different notes. So if I pull up the help menu here, you can see that we can choose what sound note we want. Not only that, but we can choose, I can choose this to be a C note or a G note, or pick your favorite note on an instrument. We can actually specify what that instrument is. We can tell it for how the time we want that note to last. Here it's going to play for 1 second. And we can do this for a variety of different instruments. I guess we did the problem specifically said it was for a guitar string, so I'm going to put a guitar in here, and we'll just run this. And hopefully you'll be able to hear this, but this is just going to play what the note would sound like on a guitar. So hopefully everybody can hear that. Since we know, so this is playing the note at middle C, and since we know that middle C corresponds to a frequency of 264 hertz, I can define the angular frequency of that note to be 2 pi times that. Again, I'm going to set my parameter values. I'm going to set my frequency to be 2 pi here, and I can sum for as many terms as I want. So I'm going to create an output sound. That's going to be my Fourier series, and I'm going to start with just the pure tone, so just one note in there. I'll just suppress the output there. So now I'm going to play the output of that. We're going to make a sound. So what does that pure tone sound like? And this is not going to sound nearly as pretty as the guitar is. And you can see that's just the pure tone, but it's at the same pitch as the guitar. Now you can get a little bit of a richer sound if I include more notes in, or more higher modes in the Fourier series approximation. So I'm going to go up to the 20th mode in my Fourier series approximation. So the different the sound quality that you hear for any given instrument depends partly how you play that instrument. So in this case, how you pluck the guitar string. So if I pluck at different spaces along the string, I'm going to get slightly different sounds because you have those higher order modes that come in and produce other vibrations that your ear can pick up. So I'm gonna let me go back to just playing the first mode once again. So I'm gonna play this. So here's what the pure tone sounds like. And if I just include a few more higher modes in there, you'll hear, you can see it's a little bit of a richer sound. Still not anywhere near where the guitar is. And part of the reason for that is it's not just how you pluck it, but it's also, what is the material made of? What's the actual instrument? So a guitar does not sound like a violin, even though they are both string instruments. And the reason for that is, we are making a a linear approximation in our wave model for the waves on that guitar string. A real guitar string has nonlinearities that are going to show up that are going to lead to the sound quality and the tonality of what a guitar sounds like, which is why you can tell, even without seeing what instrument is being played, you can tell if it's a guitar or a violin. But even still, we can start to see how different instruments look by making an audio plot of those. So we're going to make an audio plot here, and I'm going to make an audio plot, one of the output that I've made, and two of the same output, but actually let's start with doing it for a guitar, and then we'll do it for an electric piano, because I think it'll be a little easier to see for an electric piano. Okay. So for our top plot here, you can see what our Fourier series approximation is for the first 20 modes in that plucked guitar string from our homework problem here. And you can see the frequency matches up very nicely. So every time this downward hump happens, you get this peak in the guitar all the way down the list. If we do electric piano, you can see that even more clearly because the sound quality is a bit more pure for the electric piano. Pure in the sinusoidal sense, not in the musical sense. So here's the electric piano sound. And if I plot that, you can see that here. If I want to go back to a pure tone for my Fourier series approximation, we'll run that here. And you should see when I plot this, this will look much more sinusoidal here rather than rather than including the higher modes. If I run that again, you can see that looks very nicely like a sinusoid. So you can see we've done quite a few things in today's episode. So we have gone through a typical homework problem where you're using Fourier series to analyze the standing modes on a plucked string. We went through how to do that, how to make that proof using Fourier's trick. And we've also showed how to plot the amplitude and do a little bit of a deeper analysis by plotting the amplitude of those modes and showing how that, showing where you can pluck a string to suppress some of those modes. We've also done a few extra credit problems where you can see how good of an approximation Fourier series is and how it improves by including more and more terms in that approximation. We've shown an animation for what a plucked string would look like, and we've shown how to animate that. And we've also shown how you can actually play the different instrument sounds so that you can actually hear what it would sound like and not just have it be a static homework problem. You can actually figure out what this is like for a real musical instrument and what it would sound like. So that is all for today. Like the video if you liked it. Click subscribe if you'd like to see more of these. And bye-bye for now.